Hello and welcome to the session on networking basics. I am Neetu Mallan, one of the organizers of the AWS user group Madurai community. And I have been preparing for my solutions architect certification. And I've come across some good amount of material on fundamentals, and I wanted to share my learnings to the community. So this particular session will be covering network layer and transport layer of the OSI model. But before we go into all that, like the basic question to someone who is just watching this session is why is the need to learn the basics of networking? What is in it, and why are you not talking about something like EC2 or S3 or some of those services which are actually relevant in the certification? So yeah, that all that is important, okay, to write the exam. But think of it in the form of, like, if you want to actually develop something in the cloud, or if you want to architect something in the cloud, it's very essential to understand the basics of how servers communicate, how actually the information flows over the internet. Okay, so I'll just share like one of my learnings when I recently attended the Become a Solutions Architect program, which is which is conducted by a group of AWS employees who are architects, or who are very well versed in this architecting world. So when asked, like, what are the top 3 skills that that a person needs to have before starting to work on in cloud? So when that question is asked, the first thing that comes to the mind is either you think of programming languages, or algorithms, data structures, Java, Python. But surprisingly, the answer that we got from Christelle Vinot, who is one of the solutions architect in AWS, was that you need to understand the fundamentals of compute, storage, and networking. Okay, so it's not about the services. Services you can definitely learn, but what about the fundamentals of how it has been built? I mean, you're trying to kind of, just don't think of it from the perspective of a certification, but if you want to have a long-term career in AWS or in AWS cloud, then you need to understand how the fundamentals work. So the entire structure of your understanding is going to be built on this fundamentals. So that's why I wanted to emphasize on the basic part, and that's why the session is on the basics of networking. So there are a lot of documentation online also. So not going into the depths of all that, I'll just start with, I had already written a blog a few weeks earlier on the data link layer and the physical layer, which are the initial layers of the layer 1 and layer 2 of the OSI model. So I'll just give a gist of that, and then I'll continue with my presentation on the network and transport layer part. Okay, so what is the OSI model? Okay, it's an abstract model which kind of gives a what can I say? It gives a structure. So it gives a template as to how, when communication happens between two kind of machines, okay, whether they are across two different parts of the world, or within the same LAN or within the same WAN. So what are the steps that it will follow? It's like a flow chart. It will go from here to this, and how the data would be packaged. How what is the data to look like? How is it going to be transmitted? Okay, how is it going to be encoded? How is it going to be decoded? So that's all the details that forms the OSI model. It's a very abstract model. When we say abstract, it means that not all of those layers actually exist. It depends. Okay, it depends on like what layers are essential for that part of the communication. So sometimes you'll have layer 3 and layer 4 in the same infrastructure. So it does not always mean that each of that layer has to exist. It's an abstracted model, and that is usually followed. Okay, so let's talk about the basics of physical and data link layer. So physical layer is suppose we have in the 2000s and 2003 and all, when around that time when we used to play video games in cyber cafes, right? We used to have two to three lots of machines, 3 to 4 machines, which used to sync up all the computer games. Okay, the same game being played by multiple players on different machines. So how does how does that work? It could be, like, to go to the most fundamental part, most basic part of it, most basic layer would be connecting two devices on the LAN using a single cable. Okay, a copper cable, or say a fiber optic cable, or say radio frequency using your Wi-Fi and things like that. So it doesn't depend. It's about the medium. The physical layer is about the physical medium that connects to computer systems, okay, to machines. So and at that level, what happens is that it's just the flow of electrical signals in the form of ones and zeros. Okay, so if we understand what the computers actually understand 1 and 0. They do not understand all the words that we type. Say if you're typing into Google, if you're typing into a browser, say www.google.com, your computer is not going to understand that. It basically understands ones and zeros. Okay, so we'll get into the details of that in the session. But I'm talking about, the actual basic flow bit of information between two machines is in the form of electrical signals, or say radio frequency, or optical signals. So but in the end, it's all ones and zeros. Okay, so that's what it drills down to. Now if you're only using say physical layer on the machines, wherein in the cafe wherein we used to play all these video games, if you're using only the physical layer, then what would be the connectivity like? So there would be a hub, and all of those machines would be connected to it. So hub, how it works is that it's a broadcast medium. So hub, if the moment one computer wants to share information with another computer, it sends the information to the hub. And what hub does is that it's a dumb device. It will just push out information, the same information, to all the devices connected to it. So if there are 4 computers that are connected to a hub, it will send information to all those 4 devices. So what used to happen in this was that suppose that two computers are trying to communicate at the same time. So there would be collision. Okay, there's no collision control in the physical layer. So what happens is, the moment 2 computers start communicating at the same time, there is a collision, and that the information is eventually lost. Okay, so there was no collision control, and there was a loss of information. So to get rid of this, okay, there is another layer on top of this physical layer, which is called the data link layer. Now, how does data link layer function here? What data link layer does is that it has frames. Okay, it communicates using frames. So like every layer in the OSI model, what it does is that the layer above, like layer 2, is already built on top of layer 1. So layer 2 is already aware of how layer 1 communicates. That is in the form of electrical signals. So what layer 2 would do is that there is a data link layer. It will take the data that is coming from the layer on top of it, that is layer 3. It will take it, it will put it encapsulate into a frame. Okay, and that frame, it will send it to the layer below it, that is the physical layer, which will then send that information in the form of zeros and ones to the machine on the other side, which will also have a layer 1, layer 2. Okay, so that way the information reaches there in the layer 1 of the second PC, and there it will again give it to the layer 2. Layer 2 will kind of it will remove that frame. It will remove that that information, the data, the payload on that frame, and it will give it to the PC, I mean the actual PC, which has to be, to which the information has to be shared to. Okay, so that's how the communication works. So how data link layer helps in kind of removing the cons of this, the layer below it, that is the physical layer, is that it uses switches. Okay, so how that works is, in a switch there are different ports. Okay, so by ports what will happen is that it is able to unicast the information, that is, it is able to send the information only to the machine that is it is intended to. Say there are 4 PCs, PC A, B, C, and D, and PC A is trying to send information to PC C. So what was happening in the physical layer was that whatever PC A was sending, it was sent to all 3 of them. So PC B, C, and D all will get it, irrespective of whom it is intended to. Okay. So here there is an intelligence in data link layer. There will be an intelligence in the switch wherein you send some information. PC A sends it to PC C, wants it to be sent to PC C. So what will happen is that information will only be sent to PCC. It's not going to be sent to all others. Okay, so it's a unicast mode of communication, and there are specific ports, and there is a table that it has. Okay, so in that table it will maintain I'm talking about the switch. That switch will maintain as to which port PCA is connected to. So that way it will identify that where it has to send the communication. So it will know that on this port PCA is connected, on this port PCB is connected. So it has a table. So it understands if your data is coming for a specific PC, then it has to be sent on this port. Okay, so so PCA, now one thing is this: there is from one device to another device communication can happen. Same way, collision control, how does it stop that? Is basically if you're sending information, PCA is sending information, at the same time PCC is also sending information. So what happens is that it will, even if there is a collision, it will only be on that one path. Okay, so others are not going to be affected. So it is not like the entire network stops, which would have happened in case of a physical layer, because there is a multicast way of communication. So here, if PCA is intending to send it to PCC and both are trying to send at the same time, then what it will do is it will basically, when the moment the collision occurs, it will stop for some time. There will be a blackout period wherein no data would be sent. Okay, again, then PCA will be the information from PCA would be tried to send, and if there's again a kind of a collision, so again there will be a blackout. So that way, by introducing blackout period, it will reduce the time wherein there would be a collision. Okay, so it will reduce the times when that can occur. And similar, also another thing is that in case of data link layer, it uses MAC addresses. Okay, so that's how you identify one machine, that is PCA and PCC. How are you going to identify this? Is basically it will on the I told you about the table, right? So which port is connected to which PC. So in that table, it will be a MAC address table. Okay, so it will have MAC address of PCA. It will have, and which port it is connected to on the switch, and MAC address of PCB, where it is which port it is connected to on the switches, things of that kind. So what is a MAC address? MAC address is basically a unique identifier for each machine. So there is a network card in the in your device, okay, in the PC. So that network card, every company which manufactures it, it will have its own kind of identifier to identify that network card, that is called NIC. And also the network card will itself have its own number, unique number. So this is a kind of a conjunction of both. It is adding both of that. It is arrived at a MAC. It's arrived to give a MAC address of that machine. So MAC address, you need to understand that it's just a unique identifier for one PC. So it understands one device is a not just PC. It's a unique identifier for any machine, two different machines that are communicating. Each will have their own unique address, MAC addresses. Okay, so that's how you understand that. Okay, this is this is this PC and this PCA and this is PCB. Okay, so using that address. So that is data link layer 2, wherein we kind of remove the cons of the physical layer. But now, like data link layer, if it's in the same LAN, it's fine. But what happens if it is across different continents? If the device that you're trying to communicate with is, say, I'm now in India, and it's something in somewhere in Australia or US, then how do you communicate with that? I mean, you can't actually lay all these physical cables from here to America to just kind of communicate, right? That is going to be a very costly initiative. So let me share my PPT as well. Just a second. Okay, sorry for the delay. I was just trying to find the share button. Okay, so let's start with the, I've given you a gist of what the physical layer and data link layer are about. So here, now I'm going to start with the networking basics of, the second section, wherein we'll be covering network layer and transport layer. Okay, so let's go to the, okay. So as I was talking, now we understood how a layer 2 helps in removing the cons of layer 1. But what about the cons of layer 2? Okay. So layer 2 has the cons, as I said, was that now if you want to connect two devices which are across the two different parts of the world, we cannot actually go on, putting all those cables, and or say there are different, like in this picture that I've shown, there are multiple computers around the world, and each of them talk in a different, they communicate in a different protocol. Okay, so just think of the way that someone from, say, Maharashtra is trying to talk to someone from Chennai, and they don't know Hindi or English. They are just talking the local languages, that is Marathi and Tamil. What happens? So none of them is going to understand what the other person is saying because they don't understand the language, right? So the same way, two different protocols are being used here. Say there are protocols like PPP or MPLS or BGPS, border gateway protocol, or say multi-protocol layer switching or point-to-point protocols. If these protocols are in play, that is, different PCs are talking in different protocols, then how do you encode or decode information, and how do you transmit it between those devices, right? So at that time, what happens is layer 2 falls short. Okay? You cannot just depend on layer 2. There has to be additional layers on top of it, wherein we can send information, and which can help in transmitting that information from this two or three or more devices, which talk in different protocol, which communicate with different protocols, but are want to communicate information to each other. Okay, so yeah, so there comes in layer 3. What is layer 3? Layer 3 is a network layer, and what is the communication medium here? It's the IP packets. Okay, that's Internet protocol packets. So as we said, layer 1 is totally about electrical signals. Layer 2 was about sending frames. And now layer 3 is about IP packets. So let's see what IP packets are. So first, before going to IP packets, let's try to understand what IP addressing is. Okay, what does it mean when we say IP address? Okay, so now when you go to a browser and you type www.google.com, okay, when you type that, that is something that is you understand, okay, that's easy for your understanding, as human understanding. But what about a PC? It does not. What about a device? What about a machine? It does not understand www.google.com. It understands IP address. So IP address is basically same way like for any of us. Like we have a home address, right? We have an address. We'll give, if something has to be sent to us, it has to come over that address. Only then it will reach us. Same way, anything that has to go to Google server has to go to a particular address. Okay, that is what IP address is. Now let's see. Okay, so for humans, it is your URL that you type, but for the machine, it is this port, this IP address, which is kind of makes sense to it. Okay, so this are IP addresses are either given by, assigned by humans, that is as through a static IP, or by the server's own protocol, that is the dynamic IP that is given by the DHCP protocol. So it can be either way. It can be a static IP or a dynamic IP, but there has to be an IP address attached to it. Okay, so now trying to understand, as I said, right, it is, you have to know, when suppose we are trying to design a VPC or give subnets, we need to understand how IP addressing happens. Okay, how can we convert from decimal to binary notation in IP and back? What is it meant to say network portion, host portion? What does it mean to say a subnet mask? So you need, and what is the relevance of it? So to understand all that, I've also put in these sections, which will give, this might feel very fundamental, but very basic, but it is essential. And say for people who are new to cloud, or people who are new to maybe from the non-technical background, this would be very helpful. So you guys need to bear with me for this. So basically, I have just shared one IP address, that is 172.32.13.65. Okay, so this is called a dotted decimal notation. This is the decimal form of writing it, and the network portion I've highlighted in red. That is the network portion, and the 13.65 is the host portion. Okay, host, when the different devices that are connected to that network would be given different numbers from this portion. Okay, and how is this decimal form coming up? This is an IPv4. Okay, IP, there's Internet Protocol version 4 kind of an address, and it has four, like every separated by dots, right? There are 8 bits of information, 8 bits separated by dot each. So there are 4 8-bit data, 8-bit numbers. So that comes to 32 bits. So there are 4 octets. Okay, so binary representation of the first octet, if we try to see, there is 172 of the network portion. We can see that, what I've done is that I've taken from 0 to 7. Okay, that is each, each portion, like for binary, it is either 1 or 0. But for decimal equivalent, it will be 2 raised to this positions. Okay, so as we said, 8 bits. So it is from 0 to 7. So that's how I've given it. So the position is for the 8 bits of the network portion alone. There is 172 of the network portion alone. So it is from 0 to 7. And it says 2 raised to that position. Okay, so 2 raised to 0 is 1, 2 raised to 1 is 2, that way up to 128, all the way up to 128. So now trying to find what comes, what will be 170, how can we depict 172 in binary? 172 is given in decimal form. How will we show it in binary? Okay, if we want to convert from decimal to binary, how are we going to do it? So what we'll do is we'll start from left to right. Okay, first we'll check whether 172 is greater than 128 or not. Okay, so we can see that it is greater. So what we'll do, the moment we see it is greater, we'll subtract 128 from 172 and we'll put 1 in the location wherein we have the smaller number. That is 128 smaller than 172. So we'll put a 1 there, and 172 minus 128 we'll be doing. So that comes to up to 4 and 6, so around 44, right? So 44 is now, that's the remainder of it. So we subtracted the number in the 7th position. We have put a 1 there to show that that is a smaller number than the number which we are checking against, that is 172. Now going to the next part, what happens is that now the remainder of 172 minus 128, that we will check whether it is smaller than. So what you're doing, you're subtracting and you're getting the remainder portion. You're checking that remainder portion with the number in the 6th position. So 44 would be smaller than 64, right? It's not greater, smaller. The moment you find that the number you're checking against is smaller, then you have to give a 0 there. Next, you go to 32. 32, you see that it is 44 will be actually bigger than 32. So what you'll do, 44 minus 32, and you'll put a 1 here. Okay. So 44 minus 32, you'll get around 12, right? So that then you'll go to the next position, that is position number 4. There you will check, is 14 greater than 16, which is not, right? So you'll put a 0 there, and you'll move on to the next position, that is position number 3. So you'll check 14, is it greater than 6? Then yes, right? So you'll subtract from 14, you'll subtract 6, which will give you 8. And you'll put 1 there in that position because 6 was smaller than 14. Okay. Similarly, you'll go next to the portion which is at the second location, second position. You'll check 14 minus 6 was 8. 8, is it smaller than 4? So you'll get, sorry, 12. I got it wrong. So 44 minus 32 was 12. 12 minus 6 is 6, right? So 6 you are checking against 4. So 6, is it smaller than 4? No, it's greater, right? So that time you'll put 1 here. You'll subtract 6 minus 4, it is 2. Then you'll go to the next position. 2 minus 2 is 0. So until the remainder comes up to 0, you'll keep on subtracting. And the moment it comes, 2 minus 2, 2 and 2 was same, right? So you put 1 there, and next you don't have to move because it's already, you have reached the remainder of 0. So you'll put a 0 in the 0th location. So this is how you'll come up, subtracting, starting from left to right, subtracting, and then checking whether the remainder is greater or less. Okay, that's how you'll come to the binary equivalent of this decimal number. So as I've shown, so 172, 32, 13, and 65, I've shown the binary representation of each of it. So this is how you'll come, this is what your device is going to understand. Okay, the device does not understand 172, 32, 13, 65. It is actually going to understand these 8 bits of in each of those decimal locations, right? So it is essential that you understand how you can derive this. Though it looks simple, people who are not familiar with it, try to kind of bring up more IP addresses and try to convert it and check. Whether you are getting the right, binary equivalent for each of those four 8-bit numbers. So here, as I've given this step, it's the same. We just check, start with the number, check the decimal equivalent in each position. If it is greater, subtract. If it is less, if it is smaller, then put a 0 in that position. That's how you do it until you get the remainder of 0. So here, the information that I've shown is that the default VPC in AWS, whenever you get your first account, right? Whenever you sign up for a free account, you will see that in any region, in any account, okay, the IPv4 address for your VPC is going to be 172.31.0.0/16. So that is kind of a default, IP address. So what's the downside of this is that you cannot change it. Okay, you cannot. I mean, there is a limitation to how you can kind of configure this VPC. So the how in a production environment or on the client side, right? You will not have this default VPC, or even when you create your own VPCs, you will customize or you'll create custom VPCs because you want the flexibility of changing the IPv4 address. But for the default VPC, this is going to be the IPv4 CIDR range. I'll talk about CIDR in my next session. So on subnetting fundamentals, this is on the OSI model only. So let's kind of consume this information and keep it in mind. Similarly, when you have the subnets, okay, in every VPC, you'll have subnets created for against each of those availability zones that you have in that region. So for each of those default subnets also per region, per account, you'll have a suffix of a network mask of subnet mask of 20/20. Okay, so what this subnet mask means, okay, let's go on to see in the, okay, before we go to subnet mask, let's try to do the opposite of what we did just in the previous slide, right? We went from decimal to binary. Now let's try to do binary to from binary to decimal. Okay, so you have a binary representation. I mean, if you are thinking what is the relevance of this, this will come very much handy when you're trying to design your own VPC. You're trying to design your own subnets. Okay, there is a catch wherein it says that you cannot have overlapping, CIDR ranges, or you cannot have overlapping IP addresses in between in the subnets. Okay, so it is very important to understand this to be able to kind of write the decimal to binary version of your IP address and writing it back. Okay, so both of them are equally important. From decimal to binary, though it was a bit different, binary and decimal is it's quite simple. Similar to you have the position from 0 to 7 because it's going to be an 8-bit. You already know it's an 8-bit number. So you write that binary in each of those positions, like 10110010. So you write it in such a way that it fits in from 0 to 7 position. And then you find the decimal equivalent of that. That is, you say 2 raised to that number, okay? 2 raised to 1, 2 raised to 0. Things like, 2 raised to 0, 2 raised to 1, 2 raised to 2. So you write whatever 2 raised to whatever that position is, that number you're writing it here in the third row of that table. Okay, now how you get the decimal equivalent is that you add all the numbers which come up in places wherein the binary is 1. Okay, whenever the binary digit is 1, just add all those numbers. So here you can see binary digit is 1 against 2, against 16, against 32, and against 128. So when adding all those 4 numbers, you'll get 170. That's how you get the decimal equivalent of a binary number. So even whenever you're having your binary digits, you can kind of create back the IP address, and similarly from your IP address, you can create back a binary equivalent of it. So that's how it comes in handy. Okay. So what is IPv4 and IPv versus IPv6? Okay. So IPv4 has a limitation that it has around 4 billion addresses, okay, IP addresses. So now going with the world population and the number of devices that each of us has, it's very limited. Okay, it's kind of less than 1 address for 1 person. So it is not actually it cannot we actually use for all the the entire population of the world. So therein IPv6 has come in, wherein it uses hexadecimal format, and there I'm not going to go too deep into it, but there you have more number of addresses, and that's a mind-boggling number of addresses. So there you have a lot of options, and you have a lot of addresses to configure. So let's try to understand now. As we said, like network layer, it two devices across the continents, they communicate through IP packets. So what does this IP packet look like? Okay, so IPv4, in IPv4 message, you can see this. There's a source address, okay, IP address. There's a destination IP address. There's a TTL, there is time to live. There's a protocol. This protocol actually says like what is the, from the layer above, this layer 3, there's a layer 4. From layer 4, when data is flowing to layer 3, what is the protocol that it will in the destination side, when your layer 3 is giving it back to the layer 4 on the destination side, then what is the protocol to be used, to be converted to? Okay, so this is that's what it says. Then there is checksum, there is total length, those are not that relevant. And there is the data, which is the payload coming from layer 4 to layer 3. Okay. Similarly, here it is in IPv6, it is basically the source address is very big. Okay, there's 128 bits, while here we had kind of 32 bits, 4 into 8 bits each. Here it is, the source address would be 128 bits, it's quite large. Okay, so it's, and so that is 2 raised to 16. And similarly, the destination address would be also be quite large. There is a, here there's a time to live. Time to live is basically how long an IP packet has to exist. Okay, if it is being sent from one device to another, okay, over the internet, then how long can it exist in the system before it is discarded? Okay, so if your network is quite slow and there are some network related issues, then what happens is that packet would be eventually discarded, so that again the communication can be restarted or things like that. That packet can be resent later, but it has a specific, because it cannot just be on the network, right? So it will be discarded after a while. So there is a time to live for that particular packet. Similarly, here on IPv6, you have a hop limit. So it says how many hops it can make before it will be, before it can reach to its destination. Okay, so coming to what is a subnet mask. So we spoke about in IP, like in the internet protocol, right? While communicating over the internet, IP address is always used with the subnet mask. Okay, you will like when you say /16 /20, it basically gives you like what is the range and what is comprising of the network and what is comprising of the host. Okay, so on each host device, in addition to IP address, as I said, there will be a subnet mask. So in this case, the subnet mask is 255.255.0.0. So what here 255 or 255 is basically your network portion, and whatever is in zeros, okay, that is your host portion. Host portion is basically your devices which are connected into that network. Okay, so so in layer 3 devices, which are routers, okay, they understand the destination address based on this subnet. If the subnet is same, okay, the destination address is within the same network, then what it will do is that it will not go to a router, to a default gateway. It will basically put in within the same network. It will be able to communicate. It helps a router to decide whether the other device to which you're communicating is within the same network or not. Okay, so that's why the subnet mask is used. So if both have the same subnet mask, so I'll show you in the further examples. So if it is same on both the sections, say device A and device B, then the router will understand that the communication is happening on the same network, so it doesn't have to go to a default gateway to transfer that packet. So to understand that, we have a subnet mask in place. So here I've given an example, that is the previous example itself, 170.32.14.65, the subnet mask of 255.255.0.0 or a /16 suffix. So what does /16 mean is that, as I said, everything between the dots is a 8-bit number. Okay, so here the first 8 bits and the second 8 bits are used by the network. So that's why 8 plus 8, 16. That's the /16 stands for. So it means that your network portion is the first 16 bits are your network portion, and the remaining is the host portion. So even if it is not specified that it is the subnet mask is 255 or 255.0.0, but you have, along with the IP address, if you have a /16, you need to understand that the first 8 bits are going for the first 8 bits are going to be your network section, and the next 2 are going to be the host portion. Okay, so here the network, the start of the network for this IPv address, that is 170.30.14.65, is going to be 170.32.0.0. Okay. So all the devices starting from, whose IP address will fall from 0 to .0 to the network end will happen at 17.32.255.255. Now, how did we reach this number of 255? Okay, is basically by adding all those. See, I showed you like from 0 to 7. Okay, all those locations we have 2 raised to 0, 2 raised to 1, up to 128. So from 128 up to the 0th position, if we add all those numbers, we'll get 255. Okay, so 255 is the end of that network, and digit of that network. So everything will lie between 0 to 255. So as our network portion is the first 16 bits, the next 16 bits are going to be your host portion from 0 to 255. In each of those, in each of that portion, you can kind of add your host devices. Okay, so that's the network begins at 172.32.0.0 and ends at 170.32.255.255. Okay, so here the information, and like if you try to understand this against your this, right, AWS cloud, right, where it's actually essential. So you usually configure whenever you see the default security group, right? Normally when we want to configure a particular port, say this port has to receive data from this, this in this protocol, like TCP protocol, SSH is the port that you're opening up. So you say that you configure the default route of 0.0.0/0, right? So this is what it means. This is basically saying that from anywhere, the data can come from anywhere. So similarly, if you say your own IP, you give your own IP address, so it would be something in this form, right, that I've shared with you. So it would be like 172.32.14. It would be in that form, and there'll be there will be a suffix to it, like a subnet mask to it, saying that would be the CIDR range of it, right? So it is basically how traffic can be sent from anywhere to this device. So the greater the suffix, okay, then the smaller would be the host portion. What does that mean? Just a second. Sorry. So what that means is that if you have, now it is /16, okay, and your first 16 bits are occupied by the network. Now if it becomes /24, what does that mean? First three, before the dot, right, all the three numbers that are there, all of the, like 172.32.14, all of that will become the network portion, because each of them is 8 bits. So 8 plus 8 plus 8, that is 24, right? That is coming up to, so your 172.32.14 becomes your network section, and .65 becomes your host. So the moment the host portion reduces, it means that there are lesser number of devices on that network. Okay, so and in the end, if it is /32, that means that all of your or the entire IP address is made up of the network section only, because uh, all of that, when /32 means that all the 8 bits in each of that section, that followed by the dots, are going to be a part of the network portion, right? 8 into 4 would be 42, 32, sorry, 8 into 4 would be 32, and that would comprise the network portion. That means only a single device, that /32 subnet mask or suffix represents a single host device. Okay, so you have to remember that the moment the suffix keeps on it is more, the network portion increases and the host portion decreases, so number of devices on that network would reduce. Okay, okay. Now how do layer 3 devices interact with each other? How is communication transmitted over the network layer is what we'll understand next. Okay? So layer 3 devices, which are routers, they will have the intelligence to understand that the layers below it, that is layer 2 and layer 1, they know how it is functioning and what's the functionality. So it will, that's how the OSI model works. That is, every layer above, for them, the below layers are abstracted. It already has the understanding of how the below layers would work, the layers below it would work. So let's understand how do routers route information. Okay. So think of your home device. Okay, from your home PC or your laptop, you're trying to access your router. Okay. So here what happens is that, suppose your source IP is 192.168.1.0 and your destination IP is 8.8.8.8. That's you're sending data to Google. Okay. So here from your home network, you're sending the information to this router. Router, what it does, it sends it to your internet service provider's router. Okay, and from there it will have a network card on that device to understand where it has to route, like whether it will have to go to the router of the where the Google server resides, or it will have to go to another, whether it is again going to go to another default gateway, or whether it has to go to, say, for each and every path that it has to go, there will be a network card present. Okay, so here in the router, what would happen is that you will basically have this kind of a table, okay, routing table, wherein you'll have the destination address. Like for Google IP, it is this address. For for another internet service provider, it would be for this abc.com, it would be this address, and for anywhere. Okay, so if it is 0.0.0.0, it will have this address, and it will also subsequently say that next hop where it has to go. Okay, like where it has to route the information. It could be a router on that server, over that section of the network, and there you'll have to route from that. The router will then route it to the eligible server. Okay, so here what you will do, the packet would be sent, this IP packet, right? It would be sent to the router. Router will send it to the will decide on this. Router will send it to your ISP. ISP will then decide, looking at this destination address, right, where to send it next. Now here the destination. In the IP packet, as we saw earlier, there is a source address and destination address, which is basically going to be your IP address, right? So here you are saying your destination address is 8.8.8.8. So it will check as to which matches, which is the closest to this. Okay. Sorry. Just a second. Okay. So what it does is that the ISP just checks in this routing table as to which like a destination address is closest to this destination IP address that it's getting in the IP packet. Okay, so it will strip that that packet and it will check which is the source destination address. Now here, if you see 0.00.0 is like, it's vast, right? It is anywhere. So it will skip this. This does not match. 8.20.13.24, it also, and /16, right? So 8.20, it is on a different network compared, because the /16 says that 8.20 is your network portion. So that does not match with the destination IP that is on the packet that we are sending from our device. So what it will do, it will skip this also, because it is not closed. Because if it was on the same network, right, even the destination address would have, in this table would have been 8.8, starting with 8.8. It's not. So it will skip this. And then the only one which matches is 8.8.8.6/16. Okay. So it will say that, okay, this is the next hop. It is where it has to route the packet. So here, now your ISP knows where it has to send the information, which address it has to send the information to. So based on that, it will take your IP packet and it will send on that to that default gateway, and then that router will then decide, okay, this is for google.com, let's send it there. Okay. That's how the communication works. So the router has a routing table which helps it to understand where it has to route information to. Okay, let's go to the next part. Okay. All right. Now we saw that layer 3 uses IP addresses, layer 2 uses MAC addresses, and layer 1 uses electrical signals. So how, when you're sending data information from one device to another through the layer, all these 3 layers, how do you understand based on the IP address that what is the MAC address of the other destination device, right? You only have IP address with you. Then how would you understand, how would the device understand, okay, this destination address has this MAC, destination device has this MAC address. So there, address resolution protocol comes into picture. Okay, so what address resolution protocol does is that, now here, if I see there are two PCs, PC1 and PC2, okay? And here, if we see, it is, the source IP is 161.168.10.2/24. What does /24 mean? The first 3 numbers, 161, 168, and 10, entirely are the network portion. .2 is only showing your host portion. Similarly, on the destination IP, if we see, it is 161.168.10.37/24. So here also, similarly, the 161.168.10, it means that it is the entire network portion. .37 is your host portion. So both of these devices are on the same network. So for ease of understanding, I have taken both the devices on the same network, and this, as I've given, is the MAC address. Okay, so MAC address is also basically on the same network, so they have kind of the same closely the same numbers. The first that is the identifier, the organization identifier is the same. Only the two numbers, the end numbers are different, 75 and 77. So what happens when you're trying to send a packet? Okay, so you're saying packet 1, you're sending from PC1. Okay, you say that is game data, or you're saying you're sending some information to PC2. Okay, then what happens is that you will layer 3 will create an IP packet with the destination and the source address, okay, and the payload, and it will send, before it sends to layer 2, okay, on the device that is on PC1, there will be a software running which will kind of like broadcast, okay, all Fs, okay, in that is it will send all Fs to the entire network, because it's in the same network. So it will send it to the entire network, and it will ask, like, who has this IP of 161.168.10.37, which is the IP address of the destination device, right? So that is PC2. So PC1 is sending it to PC2, and the ARP, that is the software which is running on PC1, okay, that will ask, okay, it will broadcast saying, and with all F's, that is F, it will be like F dot F dot F, something like that. So with that information, it will try to send, it will ask as to who is the owner of this IP address. So the ARP, which is running on the PC2, it will also receive this. It is basically broadcasting. So all the devices on the network are going to receive it. So the moment it receives it, it will check the IP address. It belongs to PC2. Then it will say that I am 161.168.10.37, and this is my MAC address. Okay, so at this level, you get the MAC address of the destination device. This is now useful in layer 2 because everything is going to go through these 3 layers. Layer 3 is going to communicate to layer 2. Layer 2 is going to communicate to layer 1 on the source side as well as on the destination side. So here you take the packet in the layer 2. What you do, you're actually putting the packet, you're putting the source MAC address and the destination MAC address. Okay, it's I think this is a typo. So the source MAC address and the destination MAC address and the packet, and you form a frame. Okay, you form a frame in layer 2, and that frame is given to layer 1, which will then convert it to electrical signals and give it to layer 1 of the destination device, because now it knows, right, which is the destination device. So it will give it to layer 1, and layer 1, what it will do, layer 1 is basically, as we said, it is dumb. So it will send, and it will just send it to all the devices on the network, and for the PC2, it will, on the data link layer, there is a second layer, will remove that packet, and it will check the destination MAC address. So it's its own address. So what it will do, it will remove the packet and give it to a layer 3, which actually uses that packet, and that packet information, it will again, layer 3 will, on the destination side, will check, okay, is that packet belonging to me? Because in the packet there will be your destination IP address. So it will check, is the destination IP my IP address? It would be, right? So because it is intended for PC2, then it will take up that packet, the payload data that's present in that packet, and give it to the PC to actually use it. So this is how the communication happens using ARP. So ARP is basically used so that you can kind of get the MAC address of the device, so that the transition from layer 3 to layer 2 becomes smooth, because that's layer 2 only understands MAC addresses. So it needs the MAC address of the destination device so as to communicate. So that's how ARP works. Let's go to the next section. Okay. So here I'll give an understanding of how IP routing works. Okay, on a high level, say that there are 3 networks here. One is a local network that is on the same LAN. Then there are remote networks, that is, say I'm talking to someone in a different state. Okay, I'm trying to send data to a different country or different continent. Then there will be remote networks in between. So this is a simplified form. This would get more complicated the more hops a packet makes. But let's keep it simple. Let's use 3 networks only. Okay, so now here what happens, there are 3 PCs. If you see PC1, PC2, they exist in the same LAN network, and PC3 exists in a different remote network, which is far away. Let's say it's far away. So PC1 and PC2, as we see the addresses, right, IP addresses, that is 198.170.32.10/24 and 198.17.30.16/24. Now from here you need to understand, like the moment you see /24, right, what is /24? It basically says that the first 3 numbers, okay, in that, from while checking from left, okay, left to right, the first 3 numbers before the dot are your network portion. Okay? So suppose PC1 wants to communicate with PC2. Okay, what it will do, it will create a packet. First the layer 3, what we saw in the earlier slide. That way a packet would be created. It will be given to layer 2. That will be a frame wherein the packet will be embedded, and it will be sent to layer 1, right? So here, here this is the frame that I've shown, F1, P1, F1, which has P1 in it. Now that has to be sent to PC2, okay? So because it's on the same local network, how does it understand? It basically understands using the subnet mask /24. It means that both of them, the IP address of the source and the destination, both have /24. So it means that both are on the same network. So this is how it will understand how to route a packet. If it is on the, or how to route a frame. If it is on the same device, then both will have the same subnet, same CIDR and same suffix. sorry. And so because they both lie on the same network, PC1 will send that frame to PC2 directly using the mechanism that I told you guys in the last slide. Now, next what happens is that PC2 wants to now communicate with the destination address, which is 133.80.48.12/16, which is on, that is PC3, okay, that's on a different network. It is outside of its own network, okay? So if you check the subnet also, it's different, okay? So here now you understand this, here it is 198.172.32, that was the network portion. Here it is 133.80, which is the network portion. So it is clearly, on a different network. So what it will do, it will create a packet, okay? Just follow the steps which are highlighted as 1, 2, 3, 4, and 5. That's the route that it takes, okay? So one in the frame F2, which will hold the packet P2 that is being sent by layer 3 of PC2, okay? So that goes to this router R1, okay? So the router R1 has a routing table. It will see, okay, which, is it in the network where do I know this network? So it sees that in this its routing table, it does not have the destination address. Okay, it does not directly have the destination address. So what it will do in its network, it will kind of remove that frame. It will only put the packet in its network. Okay. So what happens the moment the packet is put in the network, the other router that is on that network will try to, it's listening for this packet being present. Okay, the moment it detects the presence of a packet, it will put it into a frame. Okay, and that is F3. So just understand that frames keep on changing, but the packet remains same. Okay, the moment the multiple hops it makes, the packet remains same. It just is stripped out from one frame and put into another. So here what happens in the step 2, it is because it is not that R1, the router knows that it's not in its network, it will leave that packet in the network itself. Doesn't know where to send it to. The routing table of its routing table does not have the destination IP address. So what it will do, it will leave it there. R2, the other router, right? It will pick it up. It will put it into a new frame, and then it will give it to. And then it will check in its routing table, does this exist or not? Okay, this particular IP address, the destination IP address exists or not. So then it will see that it does exist, because if you see remote network N2, wherein this R2 resides, R2 is present, that has, this R2's routing table will have the data for this network, N2 network. So what will happen? It will again strip this packet, put into a different frame, and give it to this device, PC3 device. In PC3 again, it will kind of, the layer 1 receives it, the layer 1 strips it. Layer 1 gives it to layer 2, layer 2 strips it. It takes only the packet and gives it to this PC3 of it. The actual PC3, right? The layer 3 of PC3, and layer 3 actually gives it to the device. Right? So this is how the IP routing works. This gets more complicated as the network grows, but this is a kind of a gist of it. Like in every hop, the packet remains same. The frame is kept on it's removed and it's put into another frame. along its path, and there are multiple hops that it makes, and that's why there, as I said, there's a time to live. Okay, so there is a kind of like how many seconds or how many hours it has to stay. Sorry, how many seconds or minutes it has to stay before it can be discarded. So, okay. Right. So yeah, so this is the gist of network layer. Okay, so network layer is basically what it's doing. It's helping us to communicate over the internet by creating by giving each device an identity using the IP addresses and the subnet masks, so that across networks you can understand like which network it is belonging to, and so through that way we can send information. And even if the protocol changes, right, as we had seen, what are the cons of the layer 2, we saw that it was that if there are different protocols it becomes difficult. But here if we check the IPv address format, we saw that IPv4 address format, that there is a protocol also associated to it. So if your protocol is different, even then it has a mechanism to understand. I mean, we are sending that protocol, and accordingly that according to that protocol, that packet would be changed, and I mean packet would be stripped and changed and given back, right? So there is an understanding of what the protocol is on the other side. That information is there, which was missing in your layer 2. So that information is present in case of layer 3. And this way it helps to communicate across different networks which comprise of the internet. Okay, so internet is basically made of such small local and multiple remote networks. So this is how communication happens. Okay, let's go to the next layer, which is transport layer. Okay. Okay. So here, let's try to understand what are the cons of the network layer. We saw that there is, I mean, each layer is built upon another to kind of overcome the shortcomings of the previous layer. So what are the shortcomings of network layer? So here what happens is that, as I said, there can be there can be times when the packet can be lost, right? So if there is a slowness in the network because it's going from one network to another, which is remote. So that can happen. One network is fast, another is slow, another is very slow, or another is down totally. So what happens is that packet is lost eventually, and there's no way of retrieving it back. Okay, because what happens is that you just have two IP addresses and you're sending information, but there is only one channel of communication, right, from one device to another. The moment the data is lost, there is no kind of control of how you can retrieve that packet back. So it's just one-to-one communication, and there is no way of kind of stopping a loss of data. Similarly, there are chances of packets arriving out of sync because of the different networks that it is flowing through. It can happen that due to the slowness, one packet reaches faster and the second one reaches slower. The second one takes a lot of time to the third one takes a lot of time to reach. So that way there is a lot of out of sync delivery. So that what that happens, what is the problem with that is that there is no proper communication that happens eventually between the two devices because of all these issues. So to fix the cons of the layer 3, we have layer 4 of the OSI model, which is transport layer. Okay. So in some places, transport layer and session layer, that is the layer above this, layer 5, right? Some places, both of them combine. So I'm not going to go into the details of it, but in some sections which I'll cover, you'll understand that some places both are kind of working together in conjunction with each other. So let's try to understand what are the type of protocols in this transport layer. Okay, here there are two protocols, that is TCP, okay, which is transmission control protocol, and second is user datagram protocol, which is UDP. Now TCP is used in most cases like with HTTP, HTTPS, SSH. So whenever you hear this word of TCP IP, you understand TCP IP, right? So it means that the transport layer is using the TCP protocol And the network 3 layer is, the network layer is using IP. So TCP on top of IP is what it means, TCP IP protocol. Okay. So here, then though the connection is slower, but it's very much reliable. Okay, there is, there won't be loss of information and things like that. And it opens, how it does that, there is basically a bi-directional channel. Okay, so from one device to another, there is a channel to where one device can send information, send a request, and second can send a response, and similarly vice versa. So PCA and PCB, PCA can send a request to PCB and PCB will send a response. That's a bi-directional channel, the way the communication happens. And it's a connection-based protocol. Okay, so connectivity is established first between the two devices, and then the communication takes place, or the kind of exchange of information, or all these packets takes place. So it is the commonly used protocol along with HTTP, HTTPS, SSH. Now, I've shown this diagram here, wherein we have this security group. If you check the security group, the way we create it, okay, there is a type HTTPS, SSH. For everything, there the protocol that we used commonly is TCP, okay? And there are ports 443, 22, 80. So what happens is that this protocol helps us to communicate through any of these channels like HTTPS, or you have SSH ports through which you can communicate, but the protocol which would be used would be TCP. Similarly, there is user datagram protocol, which is kind of, it's faster but is unreliable connection. And in this, there is no connection happening. Basically, it's just transfer of information. Because there is no basically there's no connection getting formed between the two devices, for no handshake between them. Let's go to the next. So how does, we saw layer 1 was using electrical signals, layer 2 was using frames, layer 3 was using IP packets. What does layer 4 use? It uses segments for communication. So segments, what they have is, now layer 2 we saw it was MAC address, layer 3 we saw it was IP address, layer 4 is basically ports. Okay, it has the source port and the destination port. What happens when using ports is that you can open multiple port. You can have multiple ports which can communicate on different ports on the source side as well. So what happens is that you have multiple applications that can communicate with each other. Okay, so it's not limited. You have HTTP, you have SSH, you have multiple SSH ports that you can configure. So that way, what happens is that you get a lot of applications on one device can talk to another, like which would not have happened in the case of network layer, because you only have IP addresses. You have no ports. You have no particular channels of communication there, right? And communication. So segments, what happens? Layer 4 hands over segments to layer 3, which encapsulate into a IP packet. Same way that it was happening for layer 3 to layer 2. Same way it will happen for the layer 4 to layer 3 also. Segments would be put into a packet. Packet would be put into a frame and given to layer 1. Now, if you see in a security group, this TCP IP protocol, right, it allows multiple channels to be opened on an EC2 instance. Now, if you are using an AMI to configure an EC2 instance, you'll see that when you come to the security group section, you have multiple ports. You can add ports. Okay, you can customize. You have these, but these are the default channels that are present, right? HTTP, HTTPS, and SSH. So basically SSH and then HTTPS, HTTP you can add on top of it. So this allows multiple forms of communication to go through from outside world to your EC2 instance. And this is possible because of the transport layer. So that's what the emphasis is here, that you are able to open all these ports and you're able to communicate through all these ports because of the transport layer being in place. So what is the structure of a TCP segment? Okay, let's see that. As we saw the structure of an IPv packet, let's see how this TCP segment structure looks like. So we have a destination port, a source port, we have a sequence number, we have an acknowledgement number, we have certain flags like URG, ACK, PSH, RST, SYN, and FIN. And there is a receive window, okay, and there is data. So not going into all of them, but let's try to check what are important details here. So source port and destination port are basically ports on both the sides. So you're communicating devices. For each side, there will be a port available. Then there's a sequence number, which is used for ordering. Like as we said, in the network layer, we do not have a way of saying this packet has been lost, right? So here we have a sequence number, which will say that, okay, this segment goes first, then this segment, 2, 3. So that way we'll have a sequence number attached to it. Okay, I'm just taking a kind of the simplest form of it. But yeah, you'll have a way of ordering. And the moment you see that you have not received one, you can again regenerate that segment, with a new number, with that same packet, and then send. So that way your data information is not lost. It can be recreated, right? That's what sequence number helps them. Acknowledgement number is basically to show the receipt of a segment in a channel. So as I said, from one PC to another, first there will be a channel open. There will be a bi-directional channel open. What does that means is that first a request would be sent, then a response would be received. That way, a bi-directional channel would be created before sending any information. Okay, so to acknowledge that, okay, I have received this request and this is my response, there has to be an acknowledgement, right? I mean, you have to receive an acknowledgement back. So that is given through this acknowledgement number. Okay. We'll see in the next slide how this helps, how the handshake actually happens. Then there are flags. Okay, this is also something I'll cover later, but this is used for this handshake between these two devices. Now, suppose that you are sending a parcel to someone, right? You need to have a receipt. You need to have a way of tracking it. So all this happens, and you have to have a way of acknowledging that, right? The other person, or like nowadays when you check, say you send something through courier, you have a way of checking, saying that, okay, yeah, you have this, the other person has received it, or it has been. So that way, to ensure all these, like this communication actually works in kind of the networking work in the transport layer. So for that, these flags are used. So it kind of is used for different kind of symbolizes different things in a handshake. We'll understand what that is. So what is the receive window doing here? So receive window is used for flow control. Okay, it says that how much, say, if your sender, okay, if your PCA is sending some information to PC2, before it starts sending information, PC2 will tell it like, okay, I am ready to receive these many bytes, not more than that. So that receive window, right, how much data I am ready to receive from you is specified earlier in the segment. So, okay, so, and how much it can receive and what amount of data it will receive is indicated in this receive window. So how does a bidirectional handshake happen between a client and a server? Like when we send, say, data, I mean, we are kind of looking up data from some, or say you have an EC2 instance and an from the outside world, or say from your PC, you're trying to kind of talk to your EC2 instance. How does it actually work? How does your virtual server and your client, like your PC, communicate, right? So what your PC would do is that first it will send a sequence, okay? Sequence CS, as we said, here there's a sequence number. So it will create, on the client side, it will create a sequence, say CS, okay? And it will send it to the server. The server will receive that CS sequence And what it will do, it will kind of create its own sequence, that is SS, and it will increment CS by 1. So CS plus 1, and that is an acknowledgement that yes, I have received your information and this is my sequence. So that way there is a synchronized plus an acknowledgement. So it is synchronizing that, okay, we have received that information, and also it is giving an acknowledgement that, okay, now we are ready for, I understand that you have sent me the information, send it back. Then the client says, okay, I have received your sequence. Okay, this is my acknowledgement. I have got your information, and it acknowledges it, and for synchronization it sends it back. And while doing that, what it will do, it will bump the server sequence by 1, that is SS plus 1, and its own sequence plus 2, so that to tell it that, okay, this is my sequence, this is the next sequence. Once we start communicating, the next sequence would be plus, plus 1 or something. This is the sequence from where it will start. And acknowledgement is basically just telling that, okay, I've received your response, and now we are ready to start a communication. So that's how, once it sends, it's a SYN, there is a for a synchronization, it will send a sequence, a SYN ACK, wherein to synchronize, it will send a sequence back. And also, because see, there's a bi-directional channel, right? You're getting information from client to server as well as from server to client. So you have to have a sequence number on both those ends. Okay? Then it will be able to communicate with each other. So that server sequence also you send, as well as the server acknowledges by bumping the number of the client sequence number by 1. Similarly, the client will send back the information by bumping its own sequence number by 2, and then acknowledging the server sequence also. And by that way, client and server communication is created between the two. So here, if we check what all message flags are there. So FIN, right? Let's take only the relevant ones, because there are many. There are like 6 to 7 of them. All of them are not relevant here for us. So FIN is basically showing the end of segments. Okay, so it is basically denoting that, okay, my from the client side, when that flag is sent, it means that, okay, my whatever I've wanted to communicate is done, and I'm not going to send any more segments after this. Okay. Acknowledgement is sent when sent by a host. It means that, okay, I've received your communication. I have got the request that you sent, or I've got the response that you have sent. So for a bi-directional handshake, both have to speak. So that's how both acknowledge the receipt of information from either end. Then there's a synchronization. So to start a handshake, you have to first send the synchronization request, so that that's the first step in creating a bi-directional channel between the two. And the CS and SS are both kind of random sequences that client and the server would generate. Okay. Okay. So how does a TCP/IP communication happen? When you're having your laptop and you're having your EC2 instance on the cloud. So how does actually communication happen? Okay. On the cloud, on your EC2 instance, you have already created, you have opened a port by number of 443, which has a TCP protocol, SSH. Okay, it's an SSH port. So SSH communication is going to happen. And on your side, on the client side, on your laptop side, you have it will create an ephemeral port. Ephemeral port is a temporary port through which you can speak. So it is like, let's assume here it is 1050. Okay. So that is created, and that's how the communication happens. So orange and pink, that is, as I said, it's a bi-directional channel. You receive information, you also send information. So that way, the communication takes place. So here, if we see, we can see that there are multiple packets that are going through here, right? Let's not go into like layer 3, layer 4, and all of it. Let's just try to understand this, that there is a packet 1 which will host the segment 1. Let's think that its sequence number is 1. Okay, it's going from the server to the client. Okay? Your EC2 instance is sending some information to your laptop. So it will send one packet with the sequence number 1 and segment 1. Packet 2 would have the sequence number 2 and segment 2, and up to 5. Okay. Now, as we spoke about the cons of network layer, if the network is low or the data is lost, then you cannot retrieve it back, right? Now, here in this case, your packet 3, which houses your segment 3, is lost somehow, say due to slowness or something. So what it will do, it will create another segment and put the same packet into it, okay, and then send it again. So that way it will remember and it will say, see here, if you see the segment, the sequence number is 3, right? So it shows that this segment was supposed to come before, but it has come now because of some data loss. Okay. So it helps you to keep that sync between the communication. Your packets are your segments are numbered in a way to understand that which packet has to come after. So you can link between those packets. You understand, the client understands that, okay, this has been lost, but it has been retrieved again. So this is after 1 and 2, I have to use 3, and then I have to use 4, and then 5. So this kind of a sequence can be formed here in the case of the transport layer. This is how TCP/IP communication helps. Let's go next. Okay, so just having a short kind of this on slide on stateful and stateless protocols. I'm not sure how many of you must have gone through security groups and NACLs. So here the part of kind of stateful and stateless is used a lot of times. Okay, so usually when your client and your server is communicating, right, as we said, it's a bidirectional channel. Okay, so it depends on whether whether the server or the host or whether the client is storing the session information or not. Okay, the host in this case will be storing, your EC2 instance is going to store information on the session information. How does this help? See, when the session is information is stored, so once a request is received, it knows that it has to reply back. If it does not get if there's no response received, then again the same request is sent. Okay, that way the state is maintained. You know that this, if you're going to receive an information and communication from a device, you also need to send back the response. So that way that state of that session would be maintained with the server. Similarly, similarly, in case of stateless protocols, what it happens is that it lives in the moment. Okay, if you're receiving an information, you give a response back. But later, if the similar channel has to be created, or similar to the same device, if you want to talk back, right? If you're receiving a request, you won't know whether you want to send the response or not. So you are not storing the kind of session information on the server side. So what happens in the cloud is that security groups, right? When we can see that there are only in the rules, when we kind of let me go back to let's go back to okay, let's try to check out a security group. This will be clearer than So coming here, let's see. Yeah. Okay. Now let's go to security groups. Segment default security. Okay. So there are inbound and outbound rules, right? So in inbound rules, if I try to edit any inbound rule, okay. Okay. So what happens is that you're saying that this SSH for the SSH protocol, you are in saying you can at this port, there is 22 port, you are allowing data from anywhere, right? So in this case, what happens is for a security group, you always mention only allow rules. You only say that, okay, allow information to flow from here. There is never a rule wherein you say, okay, from here, the information should not come. Okay. So what is happening in security groups, that in case of security groups, the information, the state of that communication is saved. So it's stateful communication kind of that it uses. It's a stateful protocol that it's using. So what happens there is that whenever you're sending information, the host is intelligent enough to understand, okay, that if it's receiving a request, it will also have to give back a response and see if it is not sending that response in this required time. Again, if that request is sent, it will understand every time that request is sent, it is going to come sorry, it's going to come from this client and have to send back a response. So there is always the communication channel is open, so it will always know that it has to send back a response. It will not, you don't have to configure a way of saying that don't send information to this client or deny access to this client, right? So going back to my screen, just a second. Yeah, so security groups are actually examples of stateful firewall. So it is basically a firewall, okay, across us outside of your EC2 instance, which actually tells that only you just need to specify allow rules, okay, what from where you have to allow data into the EC2 instance, and by default it will also understand that there is going to be a bidirectional communication. So it is, it is you do not have to explicitly specify it. It knows it. Okay, it knows it. So you don't have to specify whether you have to allow information from that client or not. It will, if you are allowing one-side communication, it knows it has to send back a response. That's why a stateful protocol, there is only one way of, it's both of those request and response are kind of added into one channel. Okay, so there is no need to specify both of them separately. It has the intelligence of understanding that a request has to follow a response and from the particular client, right? From and to the particular client. But in case of NACLs, okay, which is a term which is used for network access control list, right? In which comes up in the VPC section. So let's go back to my screen. So here, if you go to VPC, so see, for security, there are at what is it? At the instance level, you have your security groups. Okay, it works on the EC2 instance level. So outside the instance, you have security groups. But for NACLs, which are in the VPC, right? So that's across at a subnet level. Okay, the subnet is like your EC2 would be hosted in within a subnet. So at the subnet level, you have NACLs. So how do you mention NACLs? Let's go to one NACL that I have. It's the default NACL. So here, if you see, there's an allow and a deny flag. Okay, so what does it mean is that you can say that, okay, if information from this IP address can be allowed, okay, but the traffic back, you can say that inbound, outbound rules, you can say, if similarly in outbound also, you have an allow and a deny. You can say that if information from this IP address can come in, but I should not be sending a response. So you have to explicitly mention this request and response details. It's not like in security groups how it understands without you actually mentioning it. There's no allow and deny flag on a security group, right? Because everything once allowed, their bidirectional channel is created and allowed in both ways. So there is no deny part of it. But in case of a NACL, you can say allow information to come here, but deny information from that from, you can say that from this IP address 1, allow information, IP address 2, do not allow information. Similarly, you can go to a request and response level wherein you can say request can be allowed, but response should not be allowed. So that way, NACLs are stateless. So they do not understand that for them, request and response are two different stages. Even though there is a bi-directional channel, both of them are seen separately. The session information is not stored, and that's why you have these allow and deny rules for NACLs. But in the case of security groups, once allowed, it allows both ways. Okay, so let's go back to my. Sorry, yeah. So that's how stateful and stateless protocols work. So going to network address translation. Okay, now what is a NAT? Okay, like as we said, right? As I told you when we were seeing the IPv4 packets and IPv6 packets. IPv4 is basically 4 octets, that is 8 bits separated by 4 8-bit numbers, right? So binary numbers. So that if you see, there is 2 raised to 32, there are only 4 billion addresses, IP addresses. Okay, so there is a shortage of IP address because there are private IPs and there are public IPs. So private IPs are all your devices on the network, right? I mean, on your home network, you have your say your PC, your laptop. So all that have private addresses, while public addresses are used by the bigger conglomerates, which I mean, this like Google and Netflix, which you can easily access over the internet, and public addresses can be accessed over the internet. So you can talk to that public address over the internet. You can get connected, but private IP addresses you cannot directly use them on the internet. You cannot communicate on the internet directly. So how does so what happens is that this causes a shortage of IP addresses. So how do you resolve it? Okay, so we have kind of we are done with the transport layer part. Okay, and now we are starting on network address translation. What it means is that how do we remove the shortcomings of this IPv address, right, which is limited. So how do we kind of solve the shortage of these addresses? So that in that NAT comes into picture. What it does is basically there are three different types of NATs, and what it does is private addresses. It will kind of translate it into corresponding public addresses. Okay, and then you can speak over the. I mean, you can talk to them over the internet, over the devices over the internet. Okay, so when I'm communicating from my using my device, I'm communicating over internet. So there is a NAT translation happening. My router is doing a NAT translation, because of which I'm able to communicate over the internet to other, I mean, to other devices or other, say, I'm able to search through my browser, right? So all that is happening because of the NAT translation. So this is also very important because this also is used kind of at a fundamental level in the cloud, okay, in the networking section. So there are three types of NATs, that is static NAT, dynamic NAT, and port address translation. So what is static NAT? Static NAT is in case that you have, say for every private address you have, that if there is, you also have a public address. Okay, so what happens is that every kind of company, they will have this pool of addresses. So if you have equal number of IP, I mean, public and private address, what you can do is there can be one-to-one mapping. This private address you have to map to this public address. But if say you have shortage of IP addresses, okay, so there are public IP addresses are less and private addresses are more, then what do you do? Then what will happen? There will be a dynamic allocation. So it might happen that two or more devices would share the same kind of IPv address, okay, public address, but not at the same time. After one is done communicating, the second one can take up the same address and communicate. So that way it will be like there will be a one-to-one mapping. It will be basically picked up from a pool. A public address would be picked up and it can be assigned to a private, and then it will lose it, and then another device can take it, something like that. So it's one to many. So one public address can be assigned to multiple private addresses. Now port address translation, right? So port address translation, how it works is that you will be assigning different kind of many like many to one mapping. Okay, let's see in the diagram how it goes. Just a second. So in static NAT, what happens is that you have a client and you have a server. Okay, let's take a simplified version of it. There's a source IP 192.160.2.0. There is a destination IP for the server on the right, which is 10.10.2.12. Okay, both are in a different network. Now, when you're sending a packet, okay, from your PC, your own PC to this server, so what happens is that in case of static NAT, static address translation, what will happen? The router through which you're, because both are in different networks, right? So there's a router in between, and this router will have a NAT table. Okay, it will know that okay, for this private, I mean, this is a source IP coming. So what public IP I have to assign, because this client will have a private IP. So when it goes through this router, it will know that okay, this is the public IP that has to be assigned to this private IP. So when it goes out from here, like if you see the second diagram, sorry, second packet that I've shown here, the source IP is the same as the above one. Destination IP is of the destination address is that of the server. So what happens is it sends this packet P1 through this router. The source IP changes to what was the public IP here. So 22.52.12.11 would become the source IP. It would get translated to this public IP, and the destination would remain same, which is the server. So you see this flows through this, I mean, router, the source IP changes and goes to the server. Server will send back information. Okay, it sends back P2. Here the source IP would be 10.10.2.12, which was the destination IP at the source end. Okay, that becomes the source IP now because it's the server's IP address. The destination IP would become whatever is the public IP, because server was able to see only that as the source address, right? When we sent, if you see here, the source address was the public IP. So it will send it back as the destination IP. Then when it sends it back, when it goes again, it will go through the router. So router will again check the NAT table. For this public IP, what is the private IP I have? So it will be 192.160.2.0. So on that packet, it will change the IP address. It will change it to the source address. Okay, sorry, the destination IP address will be changed to the private IP, and then it would be sent to the client so that the client can recognize, okay, this is meant for me. Okay, because client is unaware of this public IP that is assigned. It knows its own IP address. So that is assigned by the router. Once it gets the response packet, it will change the destination IP on it and give it back. Now there is something called dynamic NAT. Okay. How dynamic NAT works is basically same way. There would also be a NAT table here on the router end. What happens is now there are limited number of public IPs that are available. So there are multiple sources. Okay, there is source IP of, as I said, 192.160.2.10.12.13, and all of means all at a different time instance. Say now let's think about the PC1 right here is communicating. The first client is communicating with the server. So what it does, it will again send the destination IP, its source IP, to the router. Router will check the NAT table. It knows what public IP it has to assign. So it will assign it, say 22.52.12.11. Okay, it has changed this source IP 192.168 to 22.52.12.11. And the destination IP keeping same, it will send that packet to the server. Okay. In case of say it is this PC2 and PC3 on the left end are wanting to talk to, say, Netflix, okay, which is the device which is shown here. So what happens? Both want to talk to that same device itself, and this router has only one public IP. Okay, what it will do? First, it will let PC2 talk. So source IP is 192.168.2.12 and destination IP is given 10.10.2.14. So what it will do, it will first change this source IP of this PC and assign it a public IP and send it. So public IP is 22.52.12.13 and send it to this Netflix server. Same way, now when PC3 wants to talk, it can talk only after PC2 is done with the communication, because there is shortage of public IPs, right? So both cannot talk at the same time. Once PC2 is done, PC3 will take up that same, for PC3 will the communication router will assign the same IP address and then send that information to the Netflix server. This is how communication happens in a dynamic NAT. Now let's go to port address translation. Let's go to port address translation. So here, what happens is that this totally works on different ports. Okay, so there could be same kind of ports on the destination side could be same, but source side could be same, but here the IP addresses could be same, but the ports would be different. But they will be assigned to a different port when it goes through the router. Now let's see what happens. It could be confusing when I'm saying it. So for clarity, let's see. PC1 has so in this case you use along with the IP, you'll also use a port. So the source IP here is 192.168.2.10 and port is 1050. Similarly, the destination IP is 10.10.2.12 and port is 443. Okay. And on the other end, the server side, we have to send that packet. Now on the, if you see that NAT table, right here now, it's just not about IP, there's also a port assigned. So for the first PC1, it is 92.160.2.10. The port is 1050. The public IP is going to be 22.52.12.11. Okay. And the port would be 1118. So that's how it's going to translate this IP address to a different public IP address, which is given, and a particular port 118. Okay. And it sends it to the server. So when server sends back the information, like the destination IP becomes the source IP and source IP becomes the destination IP. Now the destination IP, when it sends back the information, would be the destination IP of the public IP that has been assigned to PC1. So again, it will look up this public IP and the port would be 1118, right? There will be IP and a port in that kind of segment of information that is being sent. So there, the port, it will understand it is 1118 is corresponding to 1050 and the private IP is this. So it will route it to PC1. Now similarly, when PC2 is talking to the server, there will be, say, all this can happen at the same time, because you'll see why it is so. Here, in case of dynamic NATs, one PC and two PCs, if they are talking to the same device, and there is a IP address, public IP address crunch, so only one can talk at a time, and then the next one will talk after the first one is done with the communication. But in this case, all three can talk to the server. How it happens, we'll just see. So for PC2, the source IP is 192.160.2.12 and the port is 3211. Destination IP is 10.10.2.14, port is 443. So here, the packet goes through this router and it reaches this a server on the other end. Here, if you see the source IP is put in as 22.52.12.11. The port becomes 1119 because that's how it's been given in the NAT table. And the destination IP is that of the server, that is 10.10.2.12 and port is 443. Okay. I think there has been a mistake on this end wherein is given as at .14, but it's .12. So destination IP is same. It's of the server itself. So all three devices are communicating with the server. Okay. So here, now when the port is assigned, you can see that in the NAT table, the private IP is different. Okay, but the public IP remains same. How is it differentiated based on the port? Port varies. Okay, the public IP, the port that is assigned to the public IP keeps differing. So that's how all the three devices can communicate at the same time, because different ports are in picture. But if you see on the client side, that is all the three PCs, you can see that two devices, the PC1 and PC3, are using the same port. But in that case, the IP address is different. So that way it is quite easy to, because we have an IP and a port combination, it is easy to differentiate between the clients. Okay. So similarly, in case of packet 2, it goes from PC2, it goes to the router, it is assigned a source IP of the public IP that is given in the NAT table and the port, and is sent to the server. When it comes back, source IP becomes the destination IP. So source IP is basically your public IP of PC2 that has been assigned to PC2 by the router. That public IP would come back, that is 22.52.12. So it will check in its NAT table what is 22.52.12.11 and port 119 matching to. So it is PC2's private IP and the port. Correct. It will send it back. It will change the source IP, destination IP on this packet P3, which is coming from the server to EC2, and it will assign that particular private IP to differentiate. Similarly, now when PC3 is sending information, what it does, it looks up the NAT table. When sending data to the server, it will put the public IP and port in the source portion, and it will send it to the server. Source portion is flipped to destination while getting a response from the server, and again it will check the NAT table. What does this public IP and port stand for? It gets the private IP and port, and it routes them. The router routes them. Okay. So static NATs, what we saw, basically internet gateway. If you have worked with with VPCs, there is a concept of internet gateway, okay, which allows your kind of the instances within the VPC to communicate to the internet. Okay, all of those instances within the see whatever is the AWS private zone, right? I mean, whichever usually this EC2 instances and all, right, they will not have a private address unless you kind of configure the security groups in a way that it can communicate to the internet, right? So when you're actually designing the VPC and the instance within it, it does not have access to the internet. The internet access is given by the internet gateway. Okay? It has all these instances will have a private IP, which you actually see. Let's go back. Okay. Now, if you see here, right? See the I don't think I have an EC2 instance running. Okay, but in case of EC2, right, I do not have it running. Let me have one running. Let me launch an instance. Let's just see. So there is usually a private IP. The point that I'm trying to make here is that there is a private IP associated with your instance, right? There's a private IP associated with your instance. So it is never completely available to talk to the outside world or to the internet. So what helps it to talk to the internet is basically the internet gateway. And internet gateway uses static NAT. That is, for every private IP, there will be a public IP one-to-one mapping available, which can allow EC2 instances or any such resources which are using private IPs get a public IP to speak to the internet or to talk to the internet. Okay. And in case of NAT gateways, right, there is a concept of NAT gateways. From private IP, if you want to talk to the internet, there is a concept of using NAT gateways. So NAT gateways basically use port address translation. So what does port address translation? As we saw, there are ports involved here on the source and the destination, and there are ports involved wherein there is kind of every port is assigned to device which is going to talk. So there is the public IP would be one, but using ports you can differentiate each device which is trying to talk to the internet or talk to the outside world, outside of the AWS private zone. So this has been the end of the session on the transport and network layer, and kind of touching upon NAT and ARP as well. So this is to give you a gist of what the fundamentals of networking would look like. In case of any questions, just kind of feel free to reach out to us on our Slack group, or you can post it in the comment section of the YouTube video once it is uploaded. And that's it from my end. Thank you for listening, and thank you for watching this video, watching this session. Thank you, and have a good day.